Hey, algebra students. In this lesson, we're going to be talking about calculating frequency distributions. And you may have guessed from the title, this is another one of those probability lessons where, yeah, we're doing algebra, but we're really talking about probability and statistics a whole lot. And you may remember from probability lessons that probabilities are a measure of the likelihood of an event occurring, stated as a fraction or a percent. So let's dive right into this. The first thing we're going to do is talk about the kinds of events that we can display with frequency distributions. We're going to be looking at mostly discrete events in this lesson. Discrete events is the opposite of something called a continuous event, okay? A discrete event is an event that has a finite number of outcomes. So an example is to be rolling a dice, rolling two dice. Okay, so I can list all 36 possible combinations of two dice rolls. There's a finite countable number, 36 possible different combinations. Flipping a coin is another good example. There are two possible outcomes when flipping a coin, heads or tails. It's a discrete event because there's two possible outcomes. Now, this is in contrast to something like maybe I could measure the length of time it takes for you to sneeze. Okay. So different people are going to sneeze for different amounts of time. And there's an infinite number of different time points that I can measure that sneezes will last. Because it could be like 0.01 seconds, like if it was like 2.01 seconds, 1.0003468 seconds. And I can keep getting decimals and decimals and getting smaller and smaller, more precise values. There's an infinite number of different values that I can associate with how long it takes somebody to sneeze. There's an infinite number of values I could associate with how tall people are. Okay. Those are not discrete events, those are continuous observations. So, discrete events are ones that have a specific finite number of outcomes. We're also going to talk about compound events because this has come up quite a bit already as we've looked at statistics and probabilities. It's events that consist of two or more discrete events. Like, for example, if I flip a coin twice, that would be a compound event. What am I going to get when I flip a coin two times? All right, and then a frequency distribution is a way that we describe the possible outcomes or the experimental outcomes when we actually look at discrete events. They could also be used with continuous events too, but it makes the most sense for discrete events. So listen to this. Like if you were going to be rolling two dice, I could list all the different possible number outcomes that I could get from two dice. I could get a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, a 10, an 11, or a 12. Then I could roll my dice 100 times and count how many 2s, 3s, 4s, 5s, 6, 7, 8, 9, 10, 11, 12s I get. And I list of that 100 how many of those different outcomes are actually achieved. That would be a frequency distribution. It lists the discrete outcomes, or if using continuous data, it lists the ranges of outcomes. So, like if I was measuring people's height, I do like 4 feet to 4 feet 6, 4 feet 6 to 4 to 5 foot, 5 foot to 5 foot 6, 5 foot 6 to 6 foot, and so on. Okay. So I can list ranges of outcomes or discrete outcomes. And after several trials of an event, I record the number of times each outcome was achieved. All right, we're going to be making some frequency distributions and talking about how we can find probabilities based on frequency distributions. Let's take a look at some practice problems. So if a man bowls 5 games, keeps track of how many pins he knocks down on the first try of each turn, we can make a bar graph that shows the frequency distribution of the data. Now, here's the thing I need you to understand. This chart is a frequency distribution. So is the bar graph. The bar graph is like a picture frequency distribution. Okay. Why is this a frequency distribution? Because it shows the number of times each one of these outcomes was achieved. So here's what I'm going to do. We're going to make a horizontal table and we're going to go 1, 2, 3, 4, 5. Oh no, I forgot 0 because 0 is a possibility too. 6, 7, 8, 9, 10. Was because this is not a very nice set of data. From 0 to 10, how many numbers are there from 0 to 10? Now you're used to counting from 1 to 10. There's 10 numbers from 1 to 10. There's 11 numbers from 0 to 10. And one of the things I was asking myself as I was making this frequency distribution is, do I just make each of the individual numbers of pins its individual bar on a bar chart? Or instead, do I like group, okay, so from 0 to 1 pins, from 2 to 3 pins, from 4 to 5 pins, ranges, because I could do ranges of outcomes instead of just individual outcomes. The problem with a set of 11 data points is there's no way I can group things. I can't group them by threes because 11 doesn't divide by 3. I can't group them in pairs. I can't say 0 and 1, 2 and 3, 4 and 5, because by the time I get to 10, 10 is going to be the only number left. And the only correct way to do this is if I can group them into the same number of categories. So if I had exactly like 12 of my different data points, I could divide that into threes, and I could have ranges of 3. I can't use ranges with this because there's 11 data points, okay? So the first question is going to be, do you want to just use individual representations for each outcome at the bottom of your chart? Or do you want to group them into ranges? In this case, I can't group into ranges, so I have to use individuals. And then what I'm going to do is I'm just going to make a histogram basically that shows how many times each outcome was achieved. And this shows me something interesting. This guy must be a pretty good bowler because on his first shot, he tended to bowl 7, 8, 9, or 10. That's better than I could do. If I made a histogram of my first shots, they would definitely be favored to over on the left-hand side. So that's what we can see from this person's graph. Now, find the experimental probability of each outcome. Well, first of all, we have to ask ourselves, for probabilities, how many total trials were there? This frequency tells us how many of each different outcome we got. So there was 1, 0, 4 threes. What if I add these all up? That should give me the total number of all outcomes. 1 plus 4 is 5, 6, 7, 8 plus 6 is 14. 14 plus 17, 31. 39. 39 plus 11 is 50. So there were 50 total trials. Man bowls 5 games. That makes sense. 10 frames per game, 50 total trials for the first number of pins knocked down per frame. Okay, so that makes sense. Now, if there's 50 total trials, can I figure out a probability for each one? So 0 would be 1 over 50. 3 would be 4 over 50. By the way, 1 and 2 would be 0 over 50. For 1 over 50, 2 over 50. 2 over 50 could be simplified, by the way, to 1 over 25. 4 over 50 could be simplified to 2 over 25. 6 over 50, 17 over 50, 8 over 50, 11 over 50. So we get these probabilities as the possible outcomes. Notice they did write both 4 over 50 and 2 over 25 for the ones that were simplifiable. And those are the experimental probabilities based on the data from this guy's bowling frames. All right, student flips 2 coins. Make a table to show the possible outcomes in this experiment. Well, the way I would do that is the same way we made the coin or the dice table before. So I would do across the top tails and heads, and then down the side tails and heads. Okay, and then the outcomes would be the intersection of these two. So tails would be one possible outcome. Tails, heads. Notice I get a tails from the row, heads from here. This would be heads, tails, which is the same thing as tails, heads, and then heads, heads. Okay, so let's just read what it says. Make a table to show the possible outcomes in this experiment if you flip 2 coins. If order matters, there's 4 different outcomes. If order doesn't matter, all I care is whether it was 2 tails, 2 heads, or 1 tail and 1 heads. Then order doesn't matter, and these 2 are actually the same outcome. Now we need to find the probability of each outcome. There's 4 possible outcomes according to my table. So this one is a 1/4 probability here. This one's a 1/4 probability down here. And this one has 2 different outcomes. So 2/4 or 1/2 that I get 1 head and 1 tail. Let's see if we get the same results. So these are the possible outcomes. Okay. These are even in the same arrangement that I had them. But notice that they just put tails, heads, even if heads was first, because it doesn't matter what the order is. And then these are the possible probabilities. Heads heads is 1/4. Tails heads, there's two tails heads, so that's 2/4 or 1/2. Tails tails is 1/4. So useful to know, if you flip a coin twice, you're much more likely to get one tail and one head, compared to both tails or both heads. In fact, it's twice as likely to get one tail and one head. All right, letter D. A toddler tears off the labels on several soup cans. So we're just going to eat a can of soup for dinner, and we don't know what it is because the labels are gone. There were 6 cans of vegetable, 3 cans of tomato, 3 cans of potato, 1 can of clam chowder. One can is chosen randomly to open. Make a graph to show the frequency distribution for possible outcomes. Now listen. This first time we made a graph, it was based on experimental data where somebody actually went bowling, and recorded the frequency distribution of their different outcomes. Here, we're going to make a frequency distribution of probable outcomes. It's not experimental, it's theoretical. Okay, so we're going to make the probable outcomes, and the way we're going to do that is by starting off the same way we did before. There's no way I can group these together. I just have to list each discrete event separately. And we're going to write V for vegetable, T for tomato, P for potato, and C for clam chowder. Also, I'm going to note that up here, while there was an inherent order in the number of pins knocked down, 0, 1, 2, 3, count it up, that was a certain type of data known as, it's numerical data, right? That can be ordered from least to greatest. This is just categorical data. I can't put these in order from least to greatest or anything, because there is no least number of type of soup, right? These are just types of soup. Okay. Now, just so you know, I'm just showing it in a specific way. If you want to make this exact thing on graph paper and just shade the boxes on your graph paper that show how tall each one is, that would be fine. Or you could actually just make an XY axis. On the X axis would be vegetable, tomato, potato, clam chowder. And then on the Y axis would be the numbers 1, 2, 3, 4, 5, 6, 7. And you just make bars. You don't have to do like shaded squares. You can just do like an actual bar graph with a Y axis that shows how high it goes. All right, but this is a graph of the frequency distribution for letter D. The theoretical probability of each outcome is just going to be the number of possible outcomes for each one, divided by the total number of possible outcomes. Now let's see. I noticed there's 6, 7, 8, 9, 10, 11, 12 possible outcomes for each can of soup. So vegetable is going to be 6 out of 12, or 1/2. Tomato is going to be 3 out of 12, 1/4. Potato, 2 out of 12, 1/6. And then clam chowder is going to be 1 out of 12. Let's just make sure we did that part right. 1/4 or 3/12, 1/2 or 6/12, 1/6 or 2/12, and then 1/12. All right, and that is how you do frequency distributions. The key is counting up the total number from the frequencies recorded in the distribution, or the frequencies that are given in a word problem like this. You count up the total number, and then you divide the number of successful outcomes for each thing by that total number to get the probabilities. And then the frequency distribution is just some way of showing the different outcomes. It could be a table, could be a word problem like this. This is a frequency distribution too. More often than not, you're going to be making a table that shows the possible outcomes and how many of each outcome there are. This is the visual picture of frequency distribution.